The need to calculate instantaneous rates of change led the discoverers of calculus to investigation of the slopes of tangent lines and ultimately to the derivative, to what we call differential calculus. But they knew. You want to do popcorn? Anybody else interested in reading?
I love it.
Is your book open?
Yes, it's right here.
I couldn't see. All right, go ahead.
Okay. Oh, do I get to like pick somebody else after I read a sentence?
See, popcorn.
But they knew that derivatives revealed only half the story. In addition to the calculation method of calculus to describe how functions were changing at a given instant, they also needed a method to describe how those instantaneous changes could accumulate over an interval to produce the function. That is why they were also investigating areas under curves, an investigation that ultimately led to the second main branch of calculus called integral calculus. Annika.
Once they have the calculus for finding slopes of tangent lines and the calculus for finding areas under curves, two geometric operations that would seem to have nothing at all to do with each other, the challenge for Newton and
Leibniz.
was to prove the connection that they knew intuitively had to be there. Abby.
Was
The
one
discovery of this connection, called fundamental theorem of calculus, brought differential and integral calculus together to become the single most powerful insight mathematicians had ever acquired for understanding how the universe works. This is my
That entire paragraph was
Anybody else
two
get chills?
sentences.
What?
Maybe because I'm sitting next to the window and it's cold.
It's
You guys can move. It's actually not, there's actually like a small amount of heat coming out of this. Very small amount.
Oh, there's money on this page.
I have 2 markers.
Where?
3 markers.
Oh, yes.
Is that a 10?
That's a 10. They're burning it. Hey, I'd keep that.
Do we make
They have a 20.
You actually just asked that question. They can make 10.
It's not what I.
They make $7.
You're not recording,
What
right?
other?
Sure.
Alright, so if I had a velocity graph that was constant, it was just 6 the whole time for the first 10 seconds. If I asked you to find the area there, you would be multiplying its velocity times its time. And we get what?
60.
A rectangle.
6. Okay, so distance equals rate times time. So our rate is 6, our time is 10. So from this equation we learned in algebra, our distance would be 60. Okay, so all you have to do is, if you found the area underneath this curve from 0 to 10, if you found this area right here, that would represent the distance traveled by whatever object has a velocity of 6 over that time. Okay, so if this were in seconds and this were in meters per second, my unit would then be 60 meters. Okay, we found the area under the curve and we got a distance. So given a velocity equation, if you want to know how far an object went, so if this is my velocity equation, if I want to know how far it went, you could find this area right here. Okay, well, it works a whole lot easier when you have a rectangle. Okay, so we don't have a geometric formula to find the area under the curve of this little squiggly. Okay, so what we need to do is chop it up into a whole series of rectangles. Okay, so this is the rectangular approximation method, or RAM. Okay, so we can find like the area of that rectangle plus that rectangle plus another rectangle, and if we add all those areas up, we could have a good approximation for the area of the curve. So what would increase our precision and accuracy?
How small the rectangles are.
Right, so make them really, really small and lots of them, right? So if you find the limit of an infinite amount of rectangles between here and here, ultimately it would get you the actual area under the curve. So that's like a 5.3 topic where we find the limit and eventually becomes an integral, which is where all of this is leading. But today, all we're doing is finding the area in the curve using rectangles. Okay, so if you're given this, and let's say I want to find the area under curve for x between 0 to 4, and let's do 4 rectangles. And we're going to use LRAM. Okay, so there is LRAM, just stands for left RAM. There is RRAM, right RAM, and MRAM, middle RAM. Okay, so how to use RAM to find the area in the curve. I've updated my LEQ today. It's going to be a good lesson today.
Pro teacher. Okay, you gotta read it. How do you use RAM to find the
area under a curve.
This is when you say, what? There's LEQs over there?
I noticed it.
What is that whiteboard even for?
I want to learn who Chief Sokotoa is.
Well, we moved on. We're grabbing trig functions now.
Darn it.
Sorry.
That's no fun.
Alright, so we'll sketch of this. I'm going to factor out an x left with x. I'll factor out a negative x. So x minus 4. So I have x-intercepts at 0 and 4. It's a parabola with x-intercepts at 0 and 4. It opens down since it's negative, so it looks something like this. Okay, we're going to find the area under the curve using LRAM and 4 rectangles. So if we have 4 rectangles, I'm going to chop it up into fourths, which is just 1, 2, 3, 4. Okay, so LRAM.
What does RAM stand for again?
Rectangular approximation method. It's on the AP exam. You'll probably have one question with RAM.
Oh, wow. One question.
They might call it rectangular method. They might call it RAM. They might call it rectangular approximation method. Okay, so LRAM. What are we doing? So if we have a curve like this, we are producing rectangles where the left edge of them touch the curve. So here's another rectangle. It connects at the left side. We draw another one. You see that those are underestimates of the curve? Okay, so there's actually more area than we're getting with these rectangles. Do you think that's always going to be the case?
No, what if it's like this?
Right, so the next rectangle I'm going to draw is an overestimate. It's still an LRAM, but it's an overestimate. Okay, so LRAM means that the left edge of the rectangle touches the curve. Okay, so we're using LRAM. We're starting right here. So we're going to go up, and our first rectangle is a cute little line segment. Do you see that one does not exist there? Okay, so the next rectangle is this. The next rectangle is this. And then the next one is this. So all we have to do is find the area of those 4 rectangles, and we're done. Okay, so rectangles is just base times height. This one is nothing. All of their bases is 1 here. So how do I find this height?
Plug in 1.
Good, we plug 1 into the equation. So y of 1 is 3. So this is the point 1 comma 3. So this rectangle is 1 times 3, which is 3. Plugging in 2.
It's 4.
0?
Wait.
Y of 2 is 4, right?
Yes.
I
top.
This point right there is 2 comma 4, so 4 times 1 is 4, and y of 3, negative 9 plus 12 is 3, so this is another
3.
So our answer is 10 units squared. Okay, can you handle that?
Yeah.
What's the little symbol you drew up for the top?
Units squared. UN.
Oh,
Unit.
Okay, so let's say we wanted to do RAM.
No.
Same question, as long as I have my nice little graph on the board. We'll try the same thing with RAM. So RAM, you're going to hit with the right side. It's pretty intuitive. So if I'm going to draw the rectangles RAM style, we're going to go up until we hit it. And here's my first RAM rectangle. My next one. And then my last RAM does not exist.
It's just the same.
So yeah, if we did the math, we'd get 10 also with that. Do you think that RAM and LRAM are always going to be the same?
No.
So what makes this the same, do you think?
Symmetrical.
Good. So it's, as long as you're symmetrical, your A to B, there's the same on both sides of your symmetrical shape, then RAM and LRAM are going to be the same. So you would get 10 there. To show your work, you would do 1 times 3 plus 1 times 4 plus 1 times 3 equals 10 units squared. Okay, MRAM is a little more involved. It's more accurate, but ultimately, if we're going to have an infinite amount of rectangles, who cares how accurate you are, right? As long as you're pretty accurate and you do an infinite amount, you're still going to get the same answer. But MRAM would be the rectangle that goes up until it hits the graph, and it's right in the middle. So how do I find out how high that is?
Plug in 1/2.
Yeah, you'd have to plug in 1/2 there. You'd have to plug in 1.5 here. You'd have to plug in 2.5 here. And you'd have to plug in 3.5 here.
What's the answer?
So you'd have 4 rectangles to figure out MRAM.
So is it? You still gonna do the same answer?
That would be a different answer. More accurate than we have. All right.
For the LRAM and the RRAM, how come one of the rectangles doesn't exist?
The reason it doesn't exist is because your y values at the point of those endpoints are 0, so it doesn't exist. That's not always going to be true. I'll come back to that. That's the most confusing part of RAM is which rectangle does it exist. So I'm going to do another example. 0, 2, 4, 6, 8, and we are clearly going 10, 12, 9, 14, and 21. You really busted at the end. Take out. If some go-kart is going for the first 8 seconds, it starts off at 10 feet per second. Is that conceivable? We can do that. If I want to know how far the go-kart has traveled after 8 seconds, we can figure that out. Okay, so how far this is feet per second, and this is in seconds. How far traveled, and we'll try LRAM. Okay, so Annika said, well, does the rectangle not exist in the first one or the last one? We've learned in LRAM over there, we didn't have one to begin with. And then RRAM, we didn't have one at the end point. People never remember that stuff. They'll think the LRAM, the first one doesn't exist, or LRAM last one does exist or doesn't exist. People try to memorize. Sometimes you can memorize it. what I suggested is you always just draw a sketch. Draw a sketch of the first couple so you know what's going on. So my first point is 0, 10. I'm just going to make a sketch. And then 2, 12, then 4, 9. Okay, that's good. So my first rectangle using LRAM, I do include this first point, right? There's my first rectangle. Then here's my second rectangle. If I go all the way to the end, I might as well at this point. 2, let's see, 0, 2, 4, 6 is 14, and 8 is 21. You see that we will not use 21 for our data? 21's up there. And we aren't going to use it because we're using LRAM. And L, our rectangles begin with our left and go to the right. So this is our last rectangle. So we could have been going 1,000 at the end, but it's not going to impact the results using LRAM. Okay, so we add up the rectangles. All of them have a base of 2. So the distance is equal to 2 times 10 plus 12 plus 9 plus 14, and we leave out the 21. So 22, 31, 45, 2 times 45, 90 feet we have traveled.
So then for that one it'd be different if we did right RAM, correct?
Exactly, yep, so our RAM would be different. So using our RAM, you see my first rectangle would look like this, right? And we would ignore our first data point. Our first data point, the height of our first rectangle is actually going to be 12. And we never even used the fact that we started at 10. So our RAM, the distance, would be 2 times 12 plus 9 plus 14 plus 21. 21, 42, 56 times 212 feet. Does it make sense that we got a larger number? Because we're including the 21 and ignoring 10. Okay? Questions on that? All right, so the good news is a lot of your assignment in the future, you are going to get a calculator program that does it all for you.
Yes.
So like that over there, the parabola one, that could be done on a calculator. And the reason we could do it on a calculator is because we have an equation. But you can see that this could not be done on our calculator because we don't have an equation to input it.
Well, we couldn't make it.
Yeah, you could get into regression, but that would be like a 6-degree polynomial maybe to approximate that, and it's likely not going to be a good approximation. All right, there's a volume question at the end of your assignment I'm not going to talk about today. I might be done talking.
Yes, good.